Welcome to part two of work defined. I do remember where I left off now. In fact, I just said at the very end, it's only the component of the force that's in the direction of motion that does work. So here I go. We're going to draw that box. You know what I'm trying to do there. I didn't do a great job, but you get it. I've tried to draw a box around my vector. Anytime you do that, you know I'm going to be resolving it into its components, breaking down into its, might say X part, Y part, but in this case, I'm breaking it down into the part of, well, let's do it this way. There's a part of the force that is perpendicular to the motion, and there's a part of this force that is parallel to the motion, and it is only the parallel part that does work. Now, if we go back to our basic trig, we can see that the part of the component of the force parallel to the motion part is going to be the adjacent side of this right triangle. So work, in this case, is, well, here it is right here, but I'll just write it again because I'm just excited to talk about it, is F cosine, that's the perpendicular part, times the distance through which that force acts. And we don't usually write it that way. We're going to write it as FD cosine theta. So this is kind of our working version of this more formal cross product thing. These are the same thing, but this will, of course, will be our useful version for how we quantify work. So now let's quantify the work in this particular instance. I'm going to create a little workspace here. And let's quantify the work done in this particular situation. So I've got work equals FD cosine theta. The force was 20 newtons. The distance through which that force acted was 5 meters. And then we need to get the cosine of 30 degrees. All right, so we basically have 100 Newton meters times 0.8660, and so that's going to be 86.6 Newton meters, and that's going to be 87, and a Newton meter is a joule. So notice that it is not 100 because your force was not completely in the direction of motion. You don't get full credit for your 20 Newton force. So you did 87 joules of work. Let's look at a few more examples. A classic example in which you may be asked to calculate the work done, it's just saying you're doing the work, is you've got something on the floor or some low level, and you're given the mass of that object, and you're told, and you're going to raise it, and you're told the distance through which you're going to raise that, and the idea is how much work did you do? So let's just think about that. For you to lift this object, you're going to have to apply a certain amount of force, and that's going to be, is it FU? Let's make this F me, okay? Just, I'm going to be doing the work because I don't want to say FU too much. All right, so I'm going to have to exert a certain force, and I'm going to exert that force through a distance. These are vectors. I may not keep drawing the vector habit. These are two vectors, and I want to know how much work. So in this case, the work is FD cosine theta, but of course we see with our two vectors that there is no angle between them, so the cosine of 0 becomes 1, and so I just take my force times the distance. Now the question is what is my force? Okay, and this It may, okay, well, I'll tell you what the answer is going to be. Your force is going to be, well, what does the thing weigh? It's going to be mg. And if we just use G equals 10 newtons per kilogram, so we don't need a calculator, then your force, or my force really, because I don't want to say that, FU, is my force is going to be 500 newtons. And so we go into our basic equation here, and we say 500 newtons times the distance through which you exerted that force, 2 meters. That's going to be 1,000 Newton meters, but of course we say 1,000 joules. Now this is a really simple problem, but I find this very confusing in one respect. And let's look at a force diagram, and we'll see where my confusion lies, and hopefully we can clear it up. Let's draw a force diagram for the barbell. We're going to have the earth pulling down with a certain amount of force, and that's going to be 500 newtons. And I'm claiming, in this problem, I'm claiming that my force is going to be 500 newtons, and I can hear you already. You're saying, hey, this thing won't ever accelerate. So shouldn't my force really have to be more than 500 newtons? And the answer is yes. At the very beginning, you will have to pull up or push up with a little bit more than 500 newtons. So let me just make a force versus time diagram or chart, graph. All right, so this is my force over time. And here is the 500 Newton amount. And so at the very beginning, so when you first start to grab it, to say you begin to pull, and at the very beginning, you are going to have to pull up with a little bit more. And of course, we then realize, oh, it's going to accelerate. Well, when it gets going fast enough, you're going to go, let me clean that up here, because I want to, there's your 500. You're going to go back. Okay, so this is the speeding up phase. And then once you get it going at a certain speed, you're going to say, okay, that's fast enough. And then for a short time, you're going to be right at 500. But of course, what's going to happen at the end is you're going to want to make this thing stop, right? Your arm's only so long. So what's going to happen is at the end of the lift, you're going to actually push up with a little bit less than 500. So it turns out that if we were to look at the average force during the entire lift, it's going to be 500 newtons. So technically, this would be an average. But what's nice is it works in all cases. So in any case where you have to lift something that's not moving at the beginning, and at the end it's not moving, then your average force is going to equal to the weight. So that's how you want to calculate work whenever you're lifting something, or even pushing up a ramp. If you're pushing against gravity and it's not moving at the beginning and it's not moving at the end, then your average force will be the weight if you are lifting it straight up. If you're lifting at an angle, it's going to be, let me think about that. Okay, I thought about it, and this is what I wanted to, and this is what I mean, is that your force, but let's just do a separate problem on that one. All right, so let's move on to example 2, which is you're pushing something up a ramp. How do we quantify the work there? Before we get to the ramp problem, I want to extend the previous problem by a little bit. Okay, so now you've lifted this weight and you're done, and now you're just holding it still. How much work do you do? So you are definitely exerting a force up. and your force is going to be equal to gravity, but there's no distance through which your force is acting. You're just holding it stationary. So how much work do you do? Work is FD cosine theta. Well, I don't need to worry about the cosine theta because this guy is 0. So the work you do is going to be 0 joules. So I have a question for you is, why do you say after a few minutes, I'm getting tired, I'm starting to sweat, I'm getting hot? Why are you getting tired? Why are you sweating? Why do you get hot? Well, you're going to get hot before you start to sweat. When we say that you're not doing any work, and that's because you're not doing any work, there's no work on the barbell or the weight or what have you. There's no energy transfer to the barbell. What's happening is your muscles are doing internal work. Okay, it turns out that humans are really bad tables. Okay, so if we were to set this weight, here's a table, and if I were to set that weight on top of the table, nobody would be surprised if the table just sat there for days and days and years, many, many years, if you just left it alone, and we would never see the table get hot. So it would never get hot, it would never get tired, and so it makes perfect sense that a table isn't doing work on the barbell. But why are you getting hot? Well, it's because we have muscles that are designed to make us move, and one of the prices we pay is that our muscles are constantly firing, and that just means parts of your muscles are constantly contracting and relaxing and contracting and relaxing. And so even though it looks like you're just holding it there, if you go down and drill down to the individual muscle fibers, it's quite amazing. You can do research on this if you want, but the little muscle fibers are constantly pulling in. They're constantly pulling in one part of the muscle while they're relaxing in the next part of the muscle. And so this pulling in is actually work being done at the very, small structure scale. But none of that gets translated into work on the barbell because you're not making it go up any higher. You're not making it go faster. You're not squishing it, okay? So that's my example number 2. In this next example, we want to think about the work required to move something up a ramp. And we're going to have no friction. So mu is going to be 0. So let's just remind ourselves friction is either 0 or so small we're not going to negligible. And another thing I want to emphasize in this particular problem is that we're talking about the initial velocity right when you start pushing is going to be 0, and when this crate, this box is at the very top, it's also not going to be moving. So we're going to use that same rule, that same idea that we did in the previous problem, or the problem number 1, whatever, is, you're going to have to push up a little bit harder at the beginning, and at the end, you're going to push up with a little bit less force, so there's going to be an average force. And we'll get into that. Okay, so let's get started, and we'll talk about, I'm getting a little ahead of myself here. All right, so the work is going to be FD cosine theta. So let's think about what the D vector, of course, is going to be this guy. That's going to be your 4 meters. Your force is going to be your force. And we can see that the distance vector and the force vector are completely aligned. So the angle between them is 0. So cosine of 0 is 1. So this simplifies to just, okay, blue's fine, FU times D. Okay, now, but what is your force? And to keep this video from getting too long, I'm just going to go ahead and say, remember on ramps, let's just do it real quick here. Real quick. Here, let's do our free body diagram. And that's why there's X, and the Earth pulls down with a force of mg. And there's our angle between them. If we draw a box, that the component of gravity down the ramp is going to be, Wx. And it turns out that Wx is going to equal mg sine of the ramp angle. And so, in the end, it's going to be your work that you have to do is going to be mg sine theta times the distance. Now, this cosine relates to the angle between the applied force and the motion vector. This has to do with how big is your force going to have to be. So they're totally separate trig relationships in this case. So let's go ahead and put it in, get the values in. We've got 10 kilograms in an environment where the gravity field strength is 10 newtons per kilogram. The sine of 30 degrees is 0.5, and the distance is 4 meters. So we put that all together, and we're going to have 100 newtons times 0.5 times 4 meters, or 200 newton meters, but of course that's 200 joules. Okay, we're going to wrap this video up, and then we'll do a couple more examples in the next part 3.